Okay, lecture 52, cyclic forms of monosaccharides. And these monosaccharides will form into rings that are very, very stable. So we need to know about them. We'll talk about how stable they are later. But so if you're given a monosaccharide, D-glucose here, definitely a very important one to know as far as the rings. You need to be able to take this structure and turn it into the ring form. Now, this hydroxyl group is the one that ends up allowing the connection between this carbon, or to create the ring. So it's going to connect to this carbon and create the ring. Now, the general, let me just draw it up here, for ring systems for carbohydrates, the oxygen is always put here on the right side. That's the Hayworth projection. If you do that and you have the oxygen there as part of the ring and it's up in the upper right hand corner, then you get a lot more information as you compare different structures. So we'll always put it like that. So what we do is, since this oxygen here is going to be this oxygen, we want to curve the structure around. So we put carbon O, that's going to be this oxygen here, and I'll just flip this hydrogen up. Now this carbon is this carbon here, so this CH2OH group goes up. Now, because of the stereochemistry involved here at that site, if this is a D-glucose, that OH is on the right. If this OH were on the left, then this group would be pointing down on the other side of the ring. So that's important to remember. Now we go around. We have one carbon, 2, 3. So we're doing this, 2, 3. And then we get to, so 1, 2, 3, 4. Then we have the fifth one is the one that has the aldehyde group. Now you have an aldehyde and a hydroxyl group, and those are going to react together. Now, where do those OH groups go? The ones that are on this side, anything on this side, it goes down in the ring. Remember, the ring is going to lock it into place. So, going to lock these substituents into place. So, the ones on the right go down, the ones on the left go up. So, usually we just worry about the OH group, and a lot of times they only draw the OH group. So, we have this OH group here that's on this carbon next to the aldehyde group, goes down. Then this one goes up. Then this one goes down. You could also think of it as the hydrogen going down, but we usually deal with the OH groups. Make sure you have everything, and then you can put the other. And as I said, sometimes they don't put the hydrogens in because it's enough to have the OH groups, because you know what's on the other side for these carbohydrates. Okay, now this oxygen is going to bond here, and this hydrogen is going to go to this. It's going to break open this bond. This is an addition reaction. It's like we're adding OH to a C double bond O. We are, but they're part of the same compound, so they create a ring. All right, so now that becomes, we have this guy's CH2OH is above, carbon, 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 carbon. There's our ring. Put in the hydrogen, the OH, OH. And you can certainly do this with the line angle structures, which is normally done. You don't show everything, but I want to show everything this time. And then the OH group, as it's closing, as this ring is closing, the OH group can be above or below. Each is possible. Now, with this group above, with the oxygen here, has to be here, then the CH2OH group above, then we have, make sure that we have the, okay, yeah. So with the CH2OH group above, this is D. And with the OH group on the same side, and that's the big problem, is that it's the OH group, we're not thinking of it as being above or below the ring, we're thinking of it as on the same side or on opposite sides of the CH2OH group. That will make it beta. So this would be beta D glucose. Now I'm going to use a line angle structure. It could, or, I guess I can put it here. If I draw it smaller with the line angle, the OH could have gone down. I'll put the hydrogen here. And this is how you draw it without the hydrogens, just knowing that on the other side of that OH must be a hydrogen. Then now we have this is still D because it's above the ring, but then the OH group is across from it. And so that'd be alpha D glucose. Alright, now let's do a, if I have it here somewhere, where to put you? Alright, oh here it is, okay. Let's do, because it's not done in the book, let's close a 5-membered ring. And just trying to find all my stuff here, okay. Now here's D fructose, and it forms a ring as well. Now, this OH group is again the thing that closes the ring, and here's the C double bond to O that is going to be important too, but notice it's now, this oxygen is going to be part of the ring, 1, 2, 3, 4, 5. It's a 5-membered ring. So we have these two CH2OH groups that are going to be above or below the ring. Now, when it closes, so we have, and still these two are going to be down, and these are going to be up. So let's get the ring set up here. We'll have C, O. Now for a 5-membered ring, the oxygen sits at the top. So we have the oxygen there. We put the H here to get it out of the way, just to show the ring there. And then we have this, the double bond to the oxygen, and then we have this group. Now it looks a lot like the hydrogen here. We're going to treat this thing as if it were a hydrogen, where it can, when it closes, it can go above or below. But this group, because of the stereochemistry, the C, if it's D fructose, then the CH2OH is going to be forced up as the ring closes. But here, this CH2OH can go above or below. But let's finish this up here. Let me get everybody. Just going to put in the OH groups. Let's make sure that here's our C double bond to O, here's this guy, so this is up. That would be this carbon here is this carbon down, and we have our ring. Now it closes, and I'm just going to draw the line angle structure to keep moving here. We have the CH2OH, which that shows it's the D formation of the ring, and then we have this closes here. We got the oxygen, okay, and then the hydroxy group, and then the CH2OH is there. It's just like in the other ring where it was a hydrogen. We're still looking at this though. So this is going to be, the OH group is on the same side, so that's going to be beta D fructose. If I was saying glucose, I'm sorry, it's beta D fructose. If this had been flipped, the OH was on the opposite side, not on the bottom. Don't think of it as the bottom. The OH is across from it, then it would have been alpha D glucose. Okay. So those are 2 ring closings. Now, I made a mistake here. I drew something, I answered number 3 on this one, and I ran out of copies. Sometimes I make 2 copies of the same problem, but I ran out of both, so we're going to just cover up my mistakes with the correct answers here, or the correct start to the problem. Describe each of the following as D or L, and as alpha or beta. And I just used the 6-membered rings to show all the possibilities. Note the CH2 group is above the ring as long as the oxygen is here in upper right hand corner, and it is for each of them. The CH2OH group is to the left is above, so these are both D. And then below here, or these rings below, we have the CH2OH below, so those are L. Those would have been the ones where you have the OH group, the last OH group on the last last chiral center is on the left, would have forced these guys down. Now we have to look in comparison to them. This OH group is on the same size, so this is a beta D, and I just drew them, so I'm not exactly sure which one I've drawn here. I'm not going to worry about it. It'd just be a monosaccharide, and this would be across from it. alpha D monosaccharide. And then from here, these guys are across from each other, so this is alpha, and then these are next to each other, beta. So you should be able to look at a ring, and there's only a couple of the compounds I want you to know. The rest of them, you'd have to determine the name. I'm not going to be concerned with that on the exam for this type. I just want you to be able to tell whether it's D or L, alpha or beta. And then the last problem where are you? Okay. For D-glucose, you can see I put the D in there. It doesn't really matter. It's but how often is it found in the cyclic form? Alpha D-glucose is found 37% of the time. Beta D-glucose is found 63% of the time. That adds up to 100 because the open chain is less than 0.01%. And that's why we study these ring structures, because that's how they're normally found. The only time they're really in the open chain form, sorry, that's not exactly the greatest. In the open chain form is as they're switching from one ring formation to the other.